and also time to talk about eddy current testing. In today's video, I will be talking about why it takes so much training to become a steam generator eddy current analyst. First, I'll start by showing you the book. This is a training manual for QDA. Oh, actually, this is Level 3 study guide, wrong book. That was staged. This is actually an older, I think this is Rev 0, initial issue of the EPRI eddy current steam generator data analysis course, otherwise known as the QDA for Qualified Data Analyst. Now, if you're working in a non-nuclear environment at Joe's NDT shop, you can evaluate data most likely as a level 2. But when you're working in the nuclear world and you're doing steam generator tubing data analysis, ASME code requires that you have additional training beyond level 2 to analyze that type of data. So the Nuclear Regulatory Commission, has a lot of oversight over nuclear plants and inspections, obviously. And they want to make sure that the reactor core is kept safe. And the way that that's accomplished is by using heat removal devices known as steam generators to remove that heat from the core. To keep the steam generators doing the job right, the tubes have to be, in good shape. So it's important to inspect the tubes at regular intervals with the right techniques and have the qualified people look at that data to properly evaluate what's going on with the tubes. Now, with employer-based certification, like in the US, well, it's not all over the US, but for companies that use employer-based certification, it's kind of up to them what the training course for a data evaluator will consist of. But again, in the nuclear world, they say, hey, you gotta have the EPRI QDA, and that training is very regimented. It's very comprehensive, and it basically covers everything that an analyst could potentially come across in a day evaluating steam generator tube data. It could be from any of the 3 big nuclear steam supply system companies: Westinghouse, Combustion Engineering, Babcock and Wilcox. So it could be any of those designs. And then in those 3 NSSS vendor, they call them designs, then you have a bunch of different models of steam generators. Babcock and Wilcox, they're famous for their once-through steam generators. And the combustion engineering generators and Westinghouse generators are usually of the U-tube design, but they have a bunch of different models. They have some with preheaters, some without preheaters. Some have a baffle plate, some don't. Some have, broached hole support plates that the tubes are inserted through. Some drill hole broach holes, trifoil broaches, novafoil and nonafoil, whatever the number for 9 is, with a bunch of broaches or flow slots. And then they have different types of tubing. They could have Inconel 600, they could have thermally treated Inconel 600, they could have thermally treated Inconel 690, which is what most of the replacement steam generators have because they're less susceptible to cracking. As a matter of fact, as this video is being made, I don't know of any cracks in any steam generators around the world with Inconel 690 thermally treated tubing. They are a little bit more susceptible to mechanical wear, but that's a much more manageable damage mechanism than cracking, so we're thankful for that. So you got to look at different models of steam generators with different configurations and different tubing types. Then you also have to be trained on all the different potential types of degradation that can be found in said tubing. I probably won't get them all because I'm going by memory, but you have primary water stress corrosion cracking, which is cracking on the ID surface of the tube. Now, normally we're inspecting these tubes with bobbin probes for the bulk of the exams. And then for diagnostic purposes or to get more dispositioning information, we'll use rotating coils. The trend lately, and it's going to be the continued trend for sure, is to use an array probe to examine the tubes, because that eliminates the need to run rotating coil probes in many, many cases. So you get a lot more information than just the bobbin. But the array probes, they have a bunch of pancake coils mounted around the surface of the same body that holds the bobbin coils. So you can collect array probe data and bobbin coil data in the same probe with one pass. So that eliminates a lot of retest. So we talked about the ID, so the bobbin probe, array, you got primary water stress corrosion cracking, otherwise known as PWSCC. Then you have ODSCC, which is outside diameter stress corrosion cracking. Then we have IGA, internal granular attack, ID granular attack. What is IGA? IGA. I'm drawing a blank now, it's too early. IGA, something granular attack. Intergranular attack? Intergranular attack, that's what it is. And then we have wastage, erosion, impingement, water droplets hitting the tube. Now you wouldn't think that that could wear out a tube, but if it happens millions of times, in the same spot, it can. We've got wear fretting. Each steam generator has thousands of tubes, and when they're operating under pressure and temperature, everything's kind of like, vibrating a little bit. And as tubes vibrate against these support structures that support them, you can get some wear. Usually wear initiates and grows for a little bit, and then after a while it stabilizes. So again, that's much more easily to trend and keep an eye on and monitor and predict how it's going to act in the future. But if you get cracks, they're a little bit more unpredictable. So they're normally taken out of service, but if you have an acceptable alternate repair criteria, you may be able to run with cracks in service, depending where they're at and what your acceptance criteria is and what has been approved by the regulatory bodies. So you got PWSC, ODSC, intergranular attack, wastage, erosion, impingement, wear fretting. You can have different types of wear. You can have AVB wear, you can have tube support plate wear, and you can have wear from foreign objects. Foreign objects are the current day Achilles heel to most of the Inconel 690 tubed plants, because they don't have cracks, right? So they don't come down because of leaking tubes because of cracks. But foreign material can enter any system if you have poor housekeeping or poor foreign material controls. So analysts have to be trained to spot or detect not only foreign object wear, but the foreign objects themselves. As you know, with eddy current testing, the coil is sensitive to conductive materials. So that's not only the tube, but it's conductive materials just outside of the tube. So that could be a bolt laying on the tube sheet right next to the tube. That can be picked up by your test coil, but you have to be sort of trained to spot those kind of things. Now, you have to be trained in different types of probes. So when you get tested for the EPRI QDA, you're going to get tested on bobbin probes. You're going to get tested on plus point rotating coil probes. A few years back, the QDA was updated to include the array probe, because that was considered a new technique. Actually, array probes have been around for decades, but they had just recently, and when I say recently, it's probably been 5 years, 5, 6, 7, 8 years ago. But now everybody that's got a QDA also had to go through the array probe data sets to keep their QDA current. So when you have to analyze different types of probes, now you got to know how to set up all that stuff. So in order to use these probes, you have to calibrate them to a known standard. Somewhere around here, I've got a calibration standard for tubing. This is just a short calibration standard that's got a through wall hole and some flat bottom holes, and it's got some wear scars in this section here. But you have to collect that data with your system, and then you have to calibrate it, set the voltage normalization. You have to construct different types of curves in the software so you can correlate eddy current signal phase angle to depth, or amplitude with depth. How big is the signal? So you gotta know how to calibrate, so when you find a signal, that you can assign a depth to it if it's the type of flaw that can have a depth assigned to it. if you're finding cracks, you got to be able to length size them. So there's a specific procedure to pick the ends of the flaw and step through it, so you can do line by line flaw profiling. And then what else is there? There's another system for automated analysis. They don't go through the QDA, but automated systems have to go through the AAPDD, which is the Automated Analysis Performance Demonstration data set. So before a system can be used, it has to go to EPRI and get run through their rigorous test database to make sure that the POD is high enough for every damage mechanism. And SSPDs, which are site-specific performance demonstrations, are given to analysts every job they go to. So they basically have to prove their worthiness as an analyst at every job. And it's also good to have SSPDs to sort of get people to shift from the mindset of coming from an OTSG plant to an RSG plant, or from going from a mill and yield 600 plant that's got tons of cracks to going to a 690 thermally treated plant that doesn't have any cracks but has a lot more wear. So you got to sort of like reshift your focus. That's why they do SSPDs at every job. AAPDDs, the automated systems also have to go through a site-specific performance demonstration at every job they're deployed to, just to make sure nothing's changed and they're still working as planned. All this stuff, of course, is very well documented. And then in the steam generator analysis world, there's always lots of oversight, and there's redundant analysis passes. Normally, there's a primary pass that can be humans, or it can be one automated system. And then you have a second pass, just like having two jet engines instead of one. The second pass can either be another set of people looking at it, remote to the first set. So often they're in different states. Sometimes they're in different countries. Sometimes they're just in the room next door. But the main point is that they're separated and they're not talking, so their results remain truly independent. Then when those two sets of folks or sets of systems are completed with their analysis, that data gets run through a compare program. And then you have resolution analysts, who are usually level 3s. They look at the compared data and they look at any discrepancies between the two sets, and then they rely on the final answer. Okay, so you get to the reso. Then after the resolution is done and they have assigned the final report results, then you'll have another party come in, the independent QDA. That's a QDA just like all the other analysts that are on the job, but his specific or her specific job is to just keep an eye on what's going on in the analysis room, make sure everything's done right, and they spot check calibrations, and they look at signals or indications that were reported that were repairable or pluggable but got overridden by the reso analyst. They have to look at those, and then they randomly sample the database to just make sure the process is being performed correctly. Then you might have a utility oversight guy, a guy like me, that comes in and keeping an eye on the QDA, who's keeping an eye on the reso analyst and the production analyst. And then you might have the AI from the site. He might come in, QA might come in, check you out. Management's going to come in and check you out. The Nuclear Regulatory Commission has field inspectors that come out. They're going to be checking you out. So there's a lot of people like keeping their eye on this process, because it's an important activity, and it's important that it gets done right. So that's why the analysts have to have a high degree of training. So that's basically why it takes so much time and effort to become a data analyst. But once you get that sort of certification, if that's your goal, you'll be very sought after, because there's not a lot of qualified, certified data analysts left in the world. And I had a recent blog post showing that the eddy current and electromagnetic testing field in general is expanding pretty rapidly because of all space exploration, all the technical stuff that's going on out there. ET is a very, very highly used NDT technique just because of its versatility. It's fast, it's got immediate results. You can detect very, very minute material properties with eddy current testing. 10,000 parts an hour, no problem, like in an assembly line. Tubing, we inspect hundreds of miles of tubing in just a few days. When you're running 8 robots or 4 robots with dual guide tubes, and each guide tube's running at 40 inches a second, you can collect data fast. But the faster you collect data, the faster a large amount of data is produced that needs to be analyzed. That's why the QDA analysts are configuring and running the automated analysis systems to do a lot of the heavy lifting, doing the monotonous, same type of evaluation over and over and over. But the analysis systems will flag indications that need a closer look by the resolution team. So that's it in a nutshell. I'm going to be coming back and talking more about why it takes so long to become a level 3, because there's a lot of stuff to know there too. But that's today's video. I hope you enjoyed it. Please subscribe to this channel and like this channel. That will help me out, give me some inspiration to make more videos. And also in the comments, please ask any questions about this video, or provide suggestions for future videos, which I'll be happy to make. Enjoy your day.